Tonight, we're looking at something that has shaken the foundations of our understanding of the cosmos. 300 galaxies that, according to everything we thought we knew about the universe, should not exist. And yet, there they are, captured by the James Webb Space Telescope in images so clear, so detailed, so utterly impossible that astronomers around the world are scrambling to rewrite their theories. And by the end of tonight, you're going to understand why these galaxies are so troubling, why their existence challenges our entire model of cosmic evolution, and what it might mean for everything we thought we understood about the beginning of the universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The James Webb Space Telescope launched on December 25, 2021. It traveled for a month to reach its destination, a point in space called L2, about 1 million miles from Earth. From there, positioned beyond the Moon's orbit, shielded from the Sun's light by a tennis court-sized sunshield, it began the most ambitious mission in the history of astronomy, to peer deeper into space and further back in time than any telescope before it. Webb's primary mirror measures 21 feet across, nearly 3 times the diameter of Hubble's mirror. That size gives it 6 times the collecting area, which means it gathers 6 times more light. But more importantly, Webb observes in infrared wavelengths. This is critical because light from the most distant galaxies has been stretched by the expansion of the universe from visible light into infrared. Hubble could see some of these distant galaxies, but only barely. Webb can see them clearly, in exquisite detail, revealing structures and features that were simply invisible before. When Webb's first deep-field images were released in July 2022, they were stunning. Thousands of galaxies packed into a region of sky no larger than a grain of sand held at arm's length. Each galaxy containing billions of stars, many of them billions of light-years away. The images showed the universe in unprecedented detail. But it wasn't just the beauty that captured astronomers' attention. It was what the images revealed about the early universe. Among the thousands of galaxies in those first images, astronomers identified dozens that appeared to be extraordinarily distant, existing when the universe was less than 1 billion years old. This wasn't entirely unexpected. One of Webb's primary missions was to find these early galaxies and study how the first generation of stars and galaxies formed. What was unexpected, what sent shockwaves through the astronomical community, was how many of these early galaxies there were, and more importantly, how large and mature they appeared to be. According to our best models of galaxy formation, galaxies grow gradually over time. They start small, just a few million or billion stars, and slowly accumulate more mass through mergers with other small galaxies and by pulling in gas from their surroundings. In the first few 100 million years after the Big Bang, galaxies should be small, irregular, and relatively dim. They should look like cosmic toddlers, just beginning to take shape. But the galaxies Webb was finding didn't look like toddlers. They looked fully grown. Some of them appeared to contain tens of billions of stars. Some showed clear disk structures with organized rotation, like spiral galaxies. Some appeared to be massive elliptical galaxies with old stellar populations. These are features that should take billions of years to develop, not a few 100 million. The discovery that really crystallized the problem came in late 2022 and early 2023, as astronomers began analyzing Webb's data in detail. A team, led by Ivo Labbé from Swinburne University of Technology in Australia, identified 6 galaxies that appeared to exist between 500 million and 700 million years after the Big Bang. These galaxies, which the team nicknamed the Universe Breakers, had estimated masses between 10 billion and 100 billion times the mass of the Sun. To put that in perspective, 100 billion solar masses is roughly the mass of the entire Milky Way. And these galaxies had somehow assembled all that mass in just a few 100 million years. The problem is this. In our standard model of cosmology, called lambda CDM, structure forms hierarchically. Small things form first, then merge to make bigger things. The first stars form in mini halos, containing maybe 1 million solar masses. Those mini halos merge to form larger halos with more stars. Those merge to form small galaxies. Those small galaxies merge to form larger galaxies like the Milky Way. This process takes time, billions of years. You can't skip steps. You can't go directly from the smooth, nearly uniform distribution of matter that existed shortly after the Big Bang to a massive galaxy with 100 billion stars in just a few 100 million years. There simply isn't enough time. The math doesn't work. It's like finding a 200-pound adult in a photograph from their first birthday party. Babies don't grow that fast, and according to everything we thought we knew, neither do galaxies. But here were these observations, clear and undeniable, showing that somehow early galaxies did grow that fast. More discoveries followed throughout 2023 and into 2024. As astronomers analyzed more of Webb's data, more impossible galaxies kept appearing, not just 6, but dozens, then hundreds. A comprehensive census, published in 2024, identified over 300 galaxies in the early universe that appeared significantly more massive and mature than our models predicted. 300 is not a fluke, not an anomaly, not a few weird outliers that can be explained away. 300 is a pattern, a systematic difference between what we expected and what actually exists. The statistical analysis was clear. There are between 5 and 10 times more massive galaxies in the early universe than there should be. And they're not just slightly more massive, they're dramatically more massive, with some appearing to have accumulated more stars in a few 100 million years than should be physically possible, given the rate at which stars can form. Now, before we go further, we need to talk about how astronomers measure the age and distance of galaxies, because this is where some of the uncertainty lies. When astronomers look at a distant galaxy, they measure its spectrum, the rainbow of light it emits at different wavelengths. This spectrum contains absorption lines, dark bands where light has been absorbed by elements in the galaxy's stars. As the universe expands, space itself stretches, and this stretching affects light traveling through space. The wavelengths get longer. Blue light gets stretched toward red. Red light gets stretched into infrared. This is called redshift, and it's one of the most important concepts in cosmology. The amount of redshift tells you how much the universe has expanded since the light was emitted. And since we know how fast the universe is expanding, the redshift tells you how long the light has been traveling, which tells you how far away the galaxy is and how long ago the light was emitted. A galaxy with a redshift of 1 is about 8 billion light-years away, and we're seeing it as it was 8 billion years ago. A galaxy with a redshift of 2 is about 10.3 billion light-years away, and we're seeing it as it was 10.3 billion years ago. The highest redshift galaxies that Hubble could reliably observe had redshifts around 10 or 11, corresponding to when the universe was about 400 million to 500 million years old. Webb has now observed galaxies with redshifts of 13, 14, even possibly higher, corresponding to when the universe was less than 300 million years old. The problem is, measuring redshift precisely requires good spectroscopy, getting a detailed spectrum of the galaxy's light. But these early galaxies are extremely faint. Even with Webb's sensitivity, getting good spectra takes a long time, sometimes many hours of observation for a single galaxy. So many of the early measurements weren't spectroscopic redshifts, they were photometric redshifts. Estimates based on measuring the galaxy's brightness in several different wavelength bands and comparing to models. Photometric redshifts are faster to measure. You can estimate the redshift of hundreds or thousands of galaxies from a single image, but they're less precise. There's typically an uncertainty of about 10 to 20%, meaning a galaxy that appears to be at redshift 12 might actually be at redshift 10 or redshift 14. This uncertainty led to some early controversies. Some of the universe-breaker galaxies that appeared to be at redshift 12 or higher, based on photometric measurements, turned out to be at lower redshifts when spectroscopy was obtained. They were still distant, still interesting, but not quite as impossibly early as initially thought. But here's the important point. Even with some of the most extreme cases being revised downward, the overall pattern remains. There are still far too many massive galaxies in the early universe. The revisions moved some galaxies from absolutely impossible to merely extremely improbable, which doesn't really solve the problem. As spectroscopic observations accumulated throughout 2023 and 2024, the conclusions became firmer. Yes, some photometric redshifts were overestimates, but many were confirmed or even turned out to be underestimates. The galaxies are real, they're distant, and they're massive. By mid-2024, astronomers had spectroscopically confirmed dozens of galaxies at redshifts above 10, including several with masses exceeding 10 billion solar masses. These are not measurement errors. These are not artifacts of the data processing. These are real galaxies that really exist at times when they really shouldn't. So what's going on? There are several possibilities, and astronomers are actively debating which is correct. The first possibility is that our understanding of how to measure galaxy masses is wrong. When astronomers estimate a galaxy's mass, they're usually measuring starlight and inferring how many stars must be present to produce that much light. But this inference depends on assumptions about the stellar population, the mix of different types of stars in the galaxy. Young, massive blue stars produce far more light per unit mass than old, cool red stars. If a galaxy contains mostly blue stars, it will appear very bright for its mass. If it contains mostly red stars, it will appear dimmer. By analyzing the galaxy's spectrum and colors, astronomers try to figure out what mix of stars is present. But there's always some uncertainty. Maybe these early galaxies have stellar populations that are different from what we've assumed, containing more massive stars than expected, making them appear more massive than they really are. This would partially solve the problem, reducing the inferred masses of these galaxies. But it probably can't solve the problem entirely. Even if the mass estimates are off by a factor of 2 or 3, which would be a pretty large error, there are still too many massive galaxies. You'd need the mass estimates to be off by a factor of 5 or 10 to bring observations into agreement with models, and that seems unlikely given our understanding of stellar populations. The second possibility is that star formation in the early universe was more efficient than we thought. In the standard model, when gas collapses under gravity to form stars, only a small fraction of the gas actually makes it into stars. Most of the gas is heated by star formation and blown away before it can collapse further. This inefficiency is necessary to explain why galaxies today don't contain more stars. There's plenty of gas in the universe, but most of it never forms stars. Maybe in the early universe, conditions were different. Maybe the gas was denser, making it collapse more efficiently. Maybe there was less heavy element content, changing how gas cools and fragments. Maybe feedback from supernovas and stellar winds was less effective at preventing star formation. If star formation efficiency was higher in the early universe, galaxies could have formed stars faster, accumulating mass more quickly than our current models predict. This is plausible, but it has implications. Higher star formation efficiency would affect not just the masses of early galaxies, but also other properties like their chemical compositions and the amount of heavy elements they should contain. Astronomers are now checking these predictions against Webb's observations to see if they match. The early results are mixed. Some observations support higher star formation efficiency, others suggest it's not enough to explain the discrepancy. The third possibility is that our cosmological model is wrong. Lambda CDM, the standard model of cosmology, has been extraordinarily successful at explaining a huge range of observations. The cosmic microwave background, the large-scale structure of the universe, the expansion history, the abundance of different elements. But it's not perfect. There are a few nagging discrepancies, measurements that don't quite match predictions. The most famous is the Hubble tension, a disagreement between different methods of measuring the expansion rate of the universe. Some measurements give a value around 67 kilometers per second per megaparsec. Others give around 73 kilometers per second per megaparsec. These should agree, but they don't, and nobody knows why. Maybe lambda CDM is missing something. Maybe dark matter behaves differently than we think. Maybe dark energy isn't constant over time. Maybe there's some new physics we haven't discovered yet that affects how structures form in the early universe. If the cosmological model is wrong, it would affect our predictions for galaxy formation. Maybe structures could form faster than lambda CDM predicts, allowing galaxies to grow larger in less time. But changing the cosmological model has consequences. It would affect predictions for many other observations, not just early galaxies. Any proposed changes need to explain the new Webb observations while still matching all the other data that lambda CDM explains successfully. So far, nobody has proposed a modified cosmology that can do this cleanly. The fourth possibility is that these early galaxies are not galaxies in the usual sense, but something different. Maybe they're what astronomers call over-density regions, areas where multiple small proto-galaxies are clustered so close together that Webb's resolution can't separate them. From a distance, they look like one massive galaxy, but up close, they'd reveal themselves to be several smaller objects. This is harder to test, because it requires even higher resolution observations than Webb can provide. But some preliminary evidence suggests it might be part of the explanation. In a few cases where Webb has observed early galaxies at the highest resolution possible, the galaxies do appear to have clumpy, irregular structures, consistent with multiple merging components. But again, this probably can't explain all 300 galaxies. Some of them show clear evidence of being single, coherent objects with organized structures. The fifth possibility, and perhaps the most intriguing, is that the first stars were dramatically different from stars today. In the first few 100 million years after the Big Bang, stars formed from gas that was almost pure hydrogen and helium. No carbon, no oxygen, no iron, none of the heavy elements that exist in stars today. These heavy elements, which astronomers collectively call metals, even though most of them aren't metallic, affect how gas cools and fragments when it collapses to form stars. Without metals, gas cools less efficiently, which means the clumps that collapse to form stars are larger. This leads to more massive stars, potentially hundreds of times the mass of the Sun. These first stars, called population 3 stars, have never been observed directly. They existed too long ago and were too short-lived. Massive stars burn their fuel incredibly quickly, living only a few million years before exploding as supernovas. So population 3 stars are all long gone by now. But their existence is predicted by theory, and their supernovas would have enriched the surrounding gas with heavy elements, allowing the next generation of stars to form differently. Here's where it gets interesting. Massive stars produce far more light than smaller stars, and they also produce more heavy elements when they explode. If the first stars were predominantly very massive, they could have lit up the early universe much more brightly than expected, and enriched the gas with heavy elements much more quickly. This would allow subsequent generations of stars to form more efficiently, potentially explaining how galaxies grew so massive so quickly. Recent theoretical work suggests that the first stars might have been even more massive than previously thought, possibly reaching masses of 1,000 solar masses or more. These supermassive stars would have been extraordinarily luminous and would have had profound effects on their surroundings. Their radiation would have ionized huge volumes of gas, clearing out regions hundreds of light-years across. Their supernovas would have released tremendous amounts of energy, driving powerful shock waves that could trigger further star formation. And when they died, they might have collapsed directly into black holes without exploding, which would have interesting implications for the formation of the supermassive black holes that Webb has also found in the early universe. But we're getting ahead of ourselves. We'll come back to the black holes in a moment. Another factor that might explain the rapid growth of early galaxies is dark matter. Dark matter, the invisible substance that makes up about 85% of the matter in the universe, plays a crucial role in galaxy formation. It provides the gravitational scaffolding that pulls ordinary matter together. In the standard model, dark matter clumps under gravity to form halos, and ordinary matter falls into these halos, where it can cool, condense, and form stars. But what if dark matter in the early universe behaved differently than it does today? Some theoretical models propose that dark matter might interact with itself through forces we don't yet understand. These self-interactions would affect how quickly dark matter halos form and how dense they become. If dark matter halos formed faster or became denser in the early universe, they could have pulled in ordinary matter more efficiently, accelerating galaxy formation. This is speculative, but it's one of many ideas being explored. The advantage of dark matter explanations is that dark matter is already mysterious. We don't fully understand it. So, proposing that it behaves in unexpected ways is less radical than proposing changes to the fundamental laws of physics. But any dark matter model needs to explain not just early galaxies, but all the other observations of dark matter's effects throughout the universe. That's a high bar to clear. Now, let's talk about those supermassive black holes, because Webb has found something equally puzzling there. At the center of most large galaxies sits a supermassive black hole, an object millions or billions of times the mass of the Sun. The Milky Way's central black hole, Sagittarius A star, weighs about 4 million solar masses. The black hole at the center of the Andromeda Galaxy weighs about 100 million solar masses. The biggest black holes we know of weigh tens of billions of solar masses. These black holes are thought to grow gradually over billions of years, starting from smaller seed black holes and accumulating mass by consuming gas, dust, and occasionally entire stars. But Webb has found supermassive black holes weighing millions or even hundreds of millions of solar masses, existing when the universe was less than 1 billion years old. This presents the same problem as the massive galaxies. There simply hasn't been enough time for these black holes to grow so large. Black holes grow by accretion, pulling in matter from their surroundings. But there's a limit to how fast they can grow, a limit set by radiation pressure. As matter falls into a black hole, it heats up and emits intense radiation. This radiation pushes back against infalling matter, creating a natural limit on how fast the black hole can grow. This limit is called the Eddington limit, and for a black hole weighing 1 million solar masses, the maximum rate of growth is about 2 or 3 solar masses per year. That sounds like a lot, but over a few 100 million years, it only allows the black hole to grow by a factor of a few thousand at most. To reach millions of solar masses in the early universe, you'd need to start with seed black holes weighing thousands of solar masses, which is already quite large for a seed. And to reach hundreds of millions of solar masses, you'd need even larger seeds, or some way to exceed the Eddington limit. Webb's observations suggest that both might be happening. Some early black holes appear to be growing faster than the Eddington limit predicts, perhaps by accreting matter in bursts or through special configurations that allow them to overcome radiation pressure. And some might have started from unusually massive seeds, possibly formed from the direct collapse of massive gas clouds or from the merger of dense star clusters. The connection between supermassive black holes and their host galaxies is another piece of the puzzle. In the local universe, there's a tight relationship between the mass of a galaxy's central black hole and the mass of stars in the galaxy's bulge, the dense central region. More massive bulges contain more massive black holes, following a remarkably consistent ratio. This relationship suggests that black holes and galaxies grow together, influencing each other's evolution. But Webb's observations of early galaxies show black holes that appear to be overmassive relative to their host galaxies. The black holes weigh more than they should, given the galaxy's stellar mass. This suggests that in the early universe, black holes might have grown faster than their host galaxies, possibly getting a head start before the galaxy had assembled most of its stars. This challenges our understanding of how galaxies and black holes co-evolve and adds another layer of mystery to the problem of early galaxy formation. There's also the issue of galaxy structure. Many of the massive early galaxies that Webb has observed show signs of being disk galaxies with organized rotation, similar to spiral galaxies like the Milky Way. In the Standard Model, disk galaxies form gradually over billions of years as gas settles into a rotating disk and forms stars. In the early universe, galaxies should be more chaotic, with irregular shapes and turbulent motions. Disks take time to form because they require gas to lose energy and angular momentum, settling into a thin, rotating plane. But some of Webb's early galaxies appear to have disks already in place, just a few 100 million years after the Big Bang. This is surprising and suggests that disks can form more quickly than we thought, possibly because gas in the early universe was denser and could cool and settle more efficiently. Alternatively, maybe what looks like a disk at Webb's resolution is actually something else. Perhaps multiple merging galaxies aligned in a way that mimics a disk's appearance. Higher resolution observations will help clarify this. There's also the question of chemical enrichment. When massive stars explode as supernovas, they spread heavy elements, carbon, oxygen, silicon, iron, throughout the surrounding gas. The next generation of stars that form from this enriched gas will contain these heavy elements. By measuring the chemical composition of stars in a galaxy, astronomers can infer how many generations of stars have lived and died, enriching the gas over time. In the early universe, after only a few 100 million years, there should have been only a few generations of stars, which means galaxies should have relatively low abundances of heavy elements. But some of Webb's early galaxies show surprisingly high abundances, suggesting that many generations of stars had already lived and died. This supports the idea that star formation in the early universe was extremely rapid and efficient, cycling through multiple generations of stars in just a few 100 million years. But it also raises questions about how this rapid cycling could occur and what it means for our models of stellar evolution and chemical enrichment. It's worth stepping back and considering what all this means for cosmology and our understanding of the universe. The Big Bang model, combined with lambda CDM, has been the foundation of cosmology for decades. It explains the expansion of the universe, the cosmic microwave background, the formation of the first elements, and the large-scale structure we see today. It's been tested and refined through countless observations, and it's survived every test so far. But science advances through anomalies, through observations that don't fit the current model. Those anomalies force us to refine our theories, to dig deeper, to consider new possibilities. The massive early galaxies that Webb has found are exactly this kind of anomaly. They don't disprove the Big Bang or lambda CDM, but they show that our understanding is incomplete. There's something about the early universe that we don't fully understand yet, some process or mechanism that allowed galaxies to form faster and more efficiently than our models predict. This is exciting, not troubling. It means there's new physics to discover, new phenomena to understand. It means that despite everything we've learned about the cosmos, there are still surprises waiting for us. History shows that every major advance in telescope technology has revealed unexpected things. When Galileo first pointed a telescope at the sky in 1609, he discovered moons orbiting Jupiter, proving that not everything orbits Earth. He saw mountains on the moon, showing that celestial bodies aren't perfect spheres. He saw that the Milky Way is made of countless individual stars. Each discovery challenged prevailing ideas and expanded our understanding. When Edwin Hubble used the 100-inch Hooker telescope in the 1920s, he discovered that the universe is far larger than anyone thought, that the fuzzy nebulae, visible in small telescopes, are actually distant galaxies, and that the universe itself is expanding. This led to the Big Bang theory and revolutionized cosmology. When the Hubble Space Telescope launched in 1990, it revealed a universe filled with billions of galaxies, stretching back to within 1 billion years of the Big Bang. It showed us that galaxy formation began earlier and proceeded faster than many had expected. Now Webb is doing the same thing, pushing our observations to even earlier times and revealing a universe that's more complex, more dynamic, and more surprising than our models predicted. The massive early galaxies are not a crisis for cosmology, they're an opportunity. They're telling us that we need to refine our models, improve our understanding, and explore new ideas. Over the coming years, as more Webb data accumulates, and as astronomers develop better theories to explain these observations, we'll gain a deeper understanding of how the universe evolved from the smooth, nearly uniform state that existed shortly after the Big Bang to the rich, complex structure we see today. We'll learn how the first stars formed, how they influenced their surroundings, and how they led to the formation of the first galaxies. We'll learn how supermassive black holes grew so quickly and how they affected the galaxies around them. We'll learn whether our cosmological model needs minor adjustments or major revisions. And we'll learn whether there's new physics operating in the early universe, physics that we haven't discovered yet. This is the scientific process in action. Observation, theory, prediction, and then new observations that sometimes match predictions and sometimes surprise us. When observations surprise us, when they don't match our expectations, that's when the most interesting science happens. That's when we're forced to think harder, to question our assumptions, and to develop better theories. The 300 galaxies that Webb has discovered in the early universe, galaxies that shouldn't exist according to our models, are doing exactly this. They're forcing us to think harder about galaxy formation, star formation, dark matter, black holes, and the early universe. They're showing us that despite everything we've learned, there's still so much we don't know. And that's wonderful, because it means there's still so much left to discover. It means that future astronomers will have the opportunity to solve these mysteries, to develop new theories, to make new observations, and to push our understanding even further. It means that the story of the universe is more complex and more interesting than we imagined. Webb will continue observing for years to come, potentially decades if the mission is extended. Each new observation will add to our understanding. Spectroscopic surveys will confirm the distances and properties of these early galaxies with increasing precision. High-resolution imaging will reveal their structures in more detail. Studies of their chemical compositions will tell us about the stars they contain. Observations of the gas around them will show how they're growing and evolving. And all of this data will feed into better models, better theories, and a better understanding of how the universe works. There are also next-generation telescopes being planned that will complement Webb's observations. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter, nearly twice the size of Webb's mirror. It will observe in optical and infrared wavelengths with unprecedented resolution, able to study individual star-forming regions in distant galaxies. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will conduct wide-field surveys covering much larger areas of sky than Webb, finding thousands more distant galaxies to study. Ground-based observatories, like the Atacama Large Millimeter Array, are studying the cold gas in distant galaxies, revealing how they're accumulating the raw material for star formation. Together, these facilities will build a comprehensive picture of galaxy formation and evolution from the Big Bang to the present day. But for now, in 2026, we're in a fascinating moment. We have clear observations showing that something unexpected is happening in the early universe, but we don't yet have a clear explanation. We're in that uncomfortable but exciting space between discovery and understanding, where the data has outpaced the theory. This is where breakthroughs happen. Someone, somewhere, is going to have an insight that explains these massive early galaxies. Maybe it'll be a graduate student analyzing Webb data late at night. Maybe it'll be a veteran theorist reconsidering fundamental assumptions. Maybe it'll come from an unexpected direction, a connection nobody saw before. But it'll come, and when it does, it'll deepen our understanding of the cosmos. That's how science works. Observation drives theory. Theory makes predictions. New observations test those predictions, and the cycle continues. Each cycle brings us closer to truth, to a more accurate and complete understanding of reality. The 300 impossible galaxies that Webb has found are part of this process. They're challenges, puzzles, invitations to think more deeply and look more carefully. And in solving these puzzles, we'll learn something profound about the universe and our place in it. Because these aren't just abstract problems for professional astronomers. They're questions about the origin and evolution of galaxies, like the one we live in. The Milky Way formed through processes similar to those that formed these early galaxies, just later and more gradually. Understanding how galaxies form in the early universe helps us understand how our own galaxy formed, how the Sun and Earth came to be, and ultimately, how we came to exist. There's a direct line connecting these impossibly distant, impossibly early galaxies to you sitting here right now. The atoms in your body, the carbon, oxygen, nitrogen, calcium, iron, were forged in stars billions of years ago. Stars that formed in galaxies that were themselves the descendants of these early structures. The universe's history is your history. Its evolution is your origin story. So, when astronomers discover something surprising about the early universe, something that doesn't fit our models, they're discovering something about the conditions and processes that eventually led to your existence. That's what makes these discoveries so compelling. They're not just academic curiosities, they're chapters in the greatest story ever told. The story of how the universe evolved from simple beginnings to complex structures capable of giving rise to stars, planets, life, and consciousness. The story of how matter organized itself into patterns of increasing complexity, from subatomic particles to atoms, to molecules, to dust, to planets, to cells, to organisms, to civilizations capable of building telescopes and studying their own origins. The 300 galaxies that shouldn't exist are part of that story. They're telling us that the early chapters were more dramatic, more dynamic, more surprising than we thought. They're telling us that the universe has always been capable of exceeding our expectations. And they're reminding us that despite all our knowledge, all our sophisticated theories and powerful instruments, the universe still has the capacity to surprise us. That's humbling, but it's also inspiring. It means that no matter how much we learn, there will always be more to discover. No matter how complete our theories become, nature will always be richer, more subtle, more complex than our models capture. This should fill us with wonder and with intellectual humility. The universe is not obligated to conform to our expectations or to be easily understood. It is what it is, operating according to laws that existed long before we evolved to ponder them. Our job is to observe carefully, think clearly, and gradually refine our understanding to match reality as closely as possible. We'll never achieve perfect understanding, perfect models that capture every detail, but we can get closer, incrementally, generation by generation. And in that process, we gain not just knowledge, but wisdom. We gain perspective on our place in the cosmos and on the nature of existence itself. The James Webb Space Telescope, with its discoveries of massive early galaxies and overmassive black holes and surprisingly mature structures in the first billion years, is giving us that perspective. It's showing us a universe that formed faster and more efficiently than we expected, that was more dynamic and more complex even in its youth. It's challenging us to understand why, to figure out what we're missing, to develop better theories. And in doing so, it's advancing human knowledge in the most fundamental way possible, by revealing something new about the nature and history of the cosmos. The 300 galaxies that shouldn't exist are not mistakes, not errors, not anomalies to be explained away. They're real. They formed somehow, through processes we don't yet fully understand, in the first few 100 million years after the Big Bang. They grew massive when our models say they should have remained small. They developed structures when they should have been chaotic. They challenge our theories. Yes, but that's exactly what good observations should do. They should push the boundaries, test the limits, reveal where our understanding is incomplete. And these galaxies are doing that spectacularly. They're forcing cosmologists to reconsider fundamental assumptions about galaxy formation, star formation, dark matter, black holes, and the early universe. They're inspiring new research, new models, new observations. They're driving the field forward in exactly the way that unexpected discoveries always have. In 10 years, we'll look back on this moment as a turning point. We'll understand what allowed these galaxies to form so early and so massive. We'll have refined our models to account for Webb's observations. We'll have a more complete and accurate picture of the first billion years of cosmic history. And we'll probably have discovered new surprises, new observations that don't fit our refined models, new challenges to overcome. That's the nature of science. It's never finished, never complete. There's always another layer, another puzzle, another mystery waiting to be solved. And that's exactly as it should be. A universe that was completely understood would be a universe with no more surprises, no more discoveries, no more opportunities to expand our knowledge. How boring would that be? No. Far better to live in a universe that exceeds our grasp, that challenges our understanding, that rewards curiosity with revelation. The 300 galaxies that shouldn't exist are proof that we live in exactly such a universe. They're evidence that despite everything we've learned in the century, since Hubble discovered that the universe is expanding, we still have fundamental things to learn about how that expansion led to the structures we see today. They're reminders that the cosmos is under no obligation to be simple or easily understood. And they're invitations to keep looking, keep wondering, keep questioning, keep pushing the boundaries of human knowledge. So yes, these galaxies shouldn't exist according to our models, but they do exist. They're out there, real and physical, filled with stars and planets, and perhaps even life, existing in a universe that's more amazing, more dynamic, and more surprising than we dared imagine. And that's a beautiful thing. Thank you for joining me on this journey through the early universe and the mysteries that Webb has revealed. These are exciting times for astronomy, times when observations are challenging theories and forcing us to think more deeply about the cosmos. If you found this exploration fascinating, please like this video and subscribe to the channel. It helps me continue making these deep dives into the mysteries of space and time. And remember, every time you look up at the night sky, you're looking back in time, seeing light that left distant stars and galaxies years or even billions of years ago. Some of that light comes from galaxies that formed impossibly early, impossibly fast, in ways we don't yet understand. But we're working on it, observation by observation, theory by theory, gradually building a more complete picture of the universe and our place within it. The story of the cosmos is still being written, and the most interesting chapters may be yet to come. Good night, and keep looking up. But before we end, there's more to this story that deserves our attention. More layers to this mystery that reveal just how profound these discoveries really are. Let's talk about what these early galaxies actually look like, not just in terms of mass or distance, but in their physical appearance and what that tells us about the processes happening inside them. When Webb observes these distant galaxies, it's not just detecting faint points of light. It's actually resolving structure within the galaxies, seeing features and details that tell us about what's going on inside. Some of these early galaxies appear to be compact, dense objects, much smaller physically than the Milky Way, even though they contain comparable numbers of stars. A typical galaxy today might span 100,000 light-years across. But some of these early massive galaxies are only 10,000 or 20,000 light-years across. That means all those billions of stars are packed into a much smaller volume, creating stellar densities far higher than anything we see in local galaxies. This compact structure tells us something important. It suggests that these galaxies formed through extremely efficient processes that converted gas into stars very rapidly in a concentrated region. There wasn't time for the galaxy to spread out, to develop the extended structure we see in modern galaxies. Everything happened fast and in a relatively small space. But here's what's fascinating. Some of these compact early galaxies show signs of violent processes occurring within them. Webb's infrared observations can penetrate dust clouds that would be opaque to visible light, revealing regions of intense star formation hidden within the galaxy's core. In some cases, astronomers are detecting star formation rates of hundreds or even thousands of solar masses per year. To put that in perspective, the Milky Way currently forms about 1 or 2 new stars per year. These early galaxies are forming stars at rates hundreds of times higher. That kind of star formation doesn't happen quietly. It creates powerful stellar winds, intense radiation, and frequent supernova explosions. All of this feeds back into the surrounding gas, heating it, ionizing it, and in some cases, pushing it out of the galaxy entirely. This feedback process is crucial to understanding how galaxies evolve because it regulates how efficiently gas can continue forming stars. Too much feedback, and star formation shuts down entirely, leaving you with a dead galaxy that will never form new stars again. Too little feedback, and the galaxy converts all its gas into stars far too quickly, depleting its fuel supply and also ending up dead, just through a different process. The balance between gas inflow, star formation, and feedback is what determines how galaxies grow and evolve over time. And in these early massive galaxies, that balance appears to be different from what we see today. The star formation is more intense, the feedback is more violent, and the whole process is happening on much shorter timescales. Understanding why requires understanding the conditions in the early universe, which brings us to another important piece of the puzzle: the cosmic environment. The universe, 500 million years after the Big Bang, was very different from the universe today. For one thing, it was much smaller, only about 6% of its current size. This means everything was closer together, denser, more concentrated. Galaxies were packed more tightly, dark matter halos were closer, and the gas filling the space between galaxies was denser. This higher density had profound effects. It meant galaxies collided and merged more frequently, allowing them to grow faster through accretion. It meant gas could cool and collapse more efficiently, leading to higher star formation rates. It meant the gravitational forces pulling structures together were stronger, accelerating the formation of galaxies and galaxy clusters. But there's another crucial difference. The gas in the early universe was nearly pure hydrogen and helium. Today's universe contains significant amounts of heavier elements: carbon, oxygen, silicon, iron, all created in stars and spread through space by supernovas. These elements are crucial for many processes. They allow gas to cool more efficiently, radiating away energy so it can collapse under gravity. They allow dust to form, which shields star-forming regions from intense radiation. They're essential for forming rocky planets. But in the early universe, before many generations of stars had lived and died, these elements barely existed. The first stars and galaxies had to form from pristine gas, and this affected everything about how they formed and evolved. Pristine gas cools less efficiently than metal-enriched gas, which should make it harder for gas to collapse and form stars. But it also means the gas that does collapse forms more massive clumps, leading to more massive stars. And those massive stars, burning bright and hot, can ionize huge volumes of gas around them, affecting how subsequent stars form. This is where the story of cosmic reionization becomes relevant. In the first few 100,000 years after the Big Bang, the universe was filled with hot plasma, electrons and protons flying freely. As the universe expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, an event called recombination. For the next several 100 million years, the universe was dark, filled with neutral hydrogen gas that absorbed most radiation trying to pass through it. This period is called the Cosmic Dark Ages, and it lasted until the first stars formed. When those first stars ignited, their intense ultraviolet radiation began ionizing the hydrogen around them, creating bubbles of ionized gas in the neutral hydrogen fog. As more stars formed in more galaxies, these bubbles grew and merged, eventually overlapping until the entire universe was reionized. This process, called the epoch of reionization, occurred gradually between about 300 million and 1 billion years after the Big Bang. Webb is observing galaxies during this critical period, and what it's finding is that galaxies formed earlier and more abundantly than needed to explain reionization. The amount of ultraviolet radiation required to reionize the universe has been calculated based on observations of the cosmic microwave background and other data. And it turns out that the massive early galaxies Webb has discovered produce far more than enough radiation to accomplish reionization. In fact, there's almost an overabundance of ionizing radiation, suggesting that galaxies were incredibly efficient at producing high-energy photons in this early epoch. This connects back to the question of stellar populations. If early galaxies contained unusually massive stars, those stars would produce copious ultraviolet radiation, far more than smaller stars. This could explain both why these galaxies appear so bright and massive, and why reionization occurred when and how it did. It also raises questions about what happened to all those massive stars. Massive stars don't last long, a few million years at most, before they explode or collapse into black holes. So, the galaxies Webb is observing at 500 million or 700 million years after the Big Bang are not seeing the first generation of stars. Those stars are already gone, their remains scattered through space or locked inside black holes. What we're seeing is perhaps the second, or third, or fourth generation, stars formed from gas enriched by the supernovas of earlier stars. But those enrichment levels are still quite low compared to modern galaxies, which is part of what makes these early stellar populations so interesting and so different from what we're familiar with. Another aspect of these early galaxies that's proven surprising is their dust content. Dust, in astronomical terms, refers to tiny solid particles, mostly carbon and silicon compounds, that form when gas cools and condenses. Dust is important because it absorbs and scatters light, affecting how galaxies appear. It also provides surfaces where molecules can form, including complex organic molecules. In the local universe, galaxies contain significant amounts of dust, especially in their star-forming regions. This dust absorbs ultraviolet and visible light from stars and re-radiates it as infrared, which is part of why Webb's infrared vision is so powerful for studying star formation. But dust requires heavy elements to form, carbon and silicon particularly. In the early universe, With its lower abundances of heavy elements, there should be less dust. And indeed, most theoretical models predicted that early galaxies would be relatively dust-free. But Webb is finding dust in many of these early galaxies, sometimes in surprisingly large amounts. Some galaxies at redshift 10 or higher show clear evidence of dust, enough to significantly affect their observed colors and spectra. This is surprising because it means these galaxies have already gone through multiple generations of stars, producing heavy elements, allowing dust to form, all in just a few 100 million years. It's yet another piece of evidence that processes in the early universe operated faster and more efficiently than our models predicted. The presence of dust also affects how we interpret Webb's observations. When light from stars passes through dust, some wavelengths are absorbed more than others. Blue light scatters more easily than red light, which is why distant objects seen through dust appear reddened. This is the same phenomenon that makes sunsets red. Dust and particles in Earth's atmosphere scatter blue light away, leaving red light to reach your eye. In astronomy, this effect is called dust reddening, and it can mimic the effects of redshift. A dusty galaxy at modest distance can appear red like a more distant galaxy with little dust. Distinguishing between these effects requires careful analysis of the galaxy's spectrum, which is why spectroscopic observations are so important. Some of the early photometric redshift estimates that were later revised downward were cases where dust reddening was initially mistaken for cosmological redshift. The galaxy appeared red, suggesting it was at high redshift, but detailed spectroscopy revealed it was actually at somewhat lower redshift with significant dust content. These corrections are part of the normal scientific process. Initial estimates get refined as better data becomes available. But even accounting for these corrections, the overall picture remains. There are more massive, dusty galaxies in the early universe than our models predicted. Now, let's turn our attention to the question of how astronomers are actually trying to solve this mystery. What specific research programs and observations are underway to understand these massive early galaxies? One major effort involves obtaining detailed spectroscopy for as many of these galaxies as possible. Webb has several instruments capable of spectroscopy, splitting light into its component wavelengths to reveal absorption and emission lines from atoms and molecules in the galaxy. These spectroscopic observations take longer than simple imaging, but they provide much more information. They give precise redshifts, confirming the galaxy's distance and age. They reveal the galaxy's chemical composition, showing which elements are present and in what abundances. They measure the velocity of gas within the galaxy, showing whether it's rotating in an organized way or moving chaotically. They can detect emission from different types of regions, star-forming areas, regions around supermassive black holes, shockwaves from supernovas. All of this information helps astronomers build a complete picture of what's happening in these galaxies. Several large Webb programs are specifically devoted to spectroscopy of early galaxies. The JWST, Advanced Deep Extragalactic Survey, JADES, is one of the largest, observing a carefully selected field of sky in incredible detail. The program is obtaining spectroscopy for hundreds of galaxies at various distances, including many at redshifts above 6, corresponding to when the universe was less than 1 billion years old. Another program, the Prime Extragalactic Areas for Reionization and Lensing Science, PEARLS, is using gravitational lensing to study even more distant and faint galaxies. Gravitational lensing occurs when a massive object, like a galaxy cluster, lies between us and a more distant galaxy. The cluster's gravity bends light from the distant galaxy, magnifying it and making it appear brighter and larger than it actually is. This natural magnification allows astronomers to study galaxies that would otherwise be too faint to observe, even with Webb's sensitivity. By carefully selecting lensing clusters and observing them deeply, programs like PEARLS are finding and studying galaxies at redshifts of 13, 14, or even higher, pushing back to within 200 or 300 million years of the Big Bang. These are among the most distant objects ever observed, and they're providing crucial information about the absolute earliest phases of galaxy formation. On the theoretical side, astronomers are running increasingly sophisticated computer simulations of galaxy formation. Modern simulations can model the formation and evolution of thousands or even millions of galaxies, tracking how dark matter clumps, how gas cools and forms stars, how supernovas and black holes affect their surroundings, and how galaxies merge over time. These simulations start with initial conditions matching the early universe, tiny density fluctuations in a nearly uniform distribution of matter, and let physics do its work. By comparing simulation results to Webb's observations, astronomers can test different assumptions about star formation, efficiency, feedback processes, dark matter properties, and other parameters. If a simulation reproduces Webb's observations, matching the numbers, masses, and properties of early galaxies, that suggests the assumptions in that simulation are correct. If a simulation doesn't match observations, that tells you something is wrong with the assumptions, and you need to adjust them. This iterative process of observation, simulation, comparison, and refinement is how cosmologists develop better models of galaxy formation. Recent simulations, incorporating higher star formation efficiencies and stronger feedback from massive stars, have started to produce more massive early galaxies, bringing the simulations closer to matching Webb's observations. But there are still discrepancies, particularly at the highest masses and earliest times. No simulation yet reproduces all of Webb's observations perfectly, which tells us we're still missing something. There's also a tremendous amount of work happening in theoretical astrophysics, developing new models of star formation, stellar evolution, and feedback processes specifically for the conditions in the early universe. One area of focus is understanding how the first stars, population 3 stars, formed and evolved. These stars had no heavy elements, which affects their structure, their lifetimes, and how they die. Theoretical models suggest they could have been extraordinarily massive, and when they died, they might have created intermediate mass black holes weighing hundreds or thousands of solar masses. These black holes could serve as seeds for the supermassive black holes Webb is finding in early galaxies. Another area of focus is understanding stellar feedback in low metallicity environments. When a massive star explodes as a supernova in today's universe, with its higher heavy element abundances, the blast wave interacts with dust and gas in complex ways. But in the early universe, with little dust and few heavy elements, the feedback might have operated differently. Understanding these differences is crucial for predicting star formation rates and galaxy growth in the early universe. There's also renewed interest in alternative cosmological models, though this is more speculative. Most astronomers still think lambda CDM is fundamentally correct, and that the solution to the massive early galaxy problem lies in our incomplete understanding of astrophysical processes rather than in the science, cosmology itself. But some researchers are exploring whether modifications to dark matter properties, dark energy evolution, or even more exotic possibilities, like primordial black holes or alternative gravity theories, might explain the observations. These ideas are more radical and face higher burdens of proof. They need to explain not just Webb's observations, but all the other cosmological data we have. But it's important to explore all possibilities, even unlikely ones, because occasionally the unlikely explanation turns out to be correct. Looking forward, there are several specific observations that could help resolve the mystery of massive early galaxies. One is obtaining spectroscopy for the most massive and most distant galaxies Webb has found. Many of these galaxies have only photometric redshift so far, and getting detailed spectra will firm up their properties and allow for more precise comparisons with models. Another is studying the galaxy's internal structure at higher resolution. Webb has a resolution of about 0.1 arcseconds in the near-infrared, which sounds impressively small. But for a galaxy at redshift 10 or 12, that corresponds to physical scales of a few thousand light-years. That's enough to see the overall shape and major features, but not to resolve individual star-forming regions or to study the galaxy's dynamics in detail. Future observations, with even higher resolution, perhaps using interferometry or other advanced techniques, will reveal more about what's happening inside these galaxies. A third crucial observation is measuring the motions of gas within these galaxies. By observing emission lines from ionized gas and measuring how their Doppler shifted, astronomers can map out how the gas is moving. Is it rotating in an organized disk? Is it falling inward toward the galaxy's center? Is it being driven outward by feedback from stars or black holes? These velocity measurements reveal the dynamical state of the galaxy and provide clues about how it formed and how it's evolving. Webb has the capability to make these measurements, but it requires long integration times and careful analysis. As more data accumulates, we'll build up a clearer picture. There's also value in studying the environments around these massive early galaxies. Are they isolated, forming in relative isolation in the early universe? Or are they located in dense regions, perhaps early protoclusters where multiple galaxies are forming close together? The environmental context affects how galaxies evolve, because galaxies in dense regions can merge more easily and can feed on gas from their surroundings more efficiently. Initial observations suggest that at least some of the most massive early galaxies are indeed located in overdense regions, which might partially explain how they grew so large so quickly. But more systematic surveys are needed to determine whether this is a general pattern or just true for some fraction of massive early galaxies. Another important question is what happened to these massive early galaxies over the subsequent billions of years. Are they the progenitors of today's most massive elliptical galaxies? Or did something happen to them? Perhaps they merged with other galaxies or were disrupted by environmental effects. By studying galaxies across a range of redshifts, from the highest redshifts Webb can observe down to redshift 0, the present day, astronomers can trace how galaxy populations evolve over cosmic time. This archaeological approach, looking at galaxies at different ages and piecing together the history, is revealing how the galaxy population has changed over the last 13 billion years. What we're finding is that massive galaxies at high redshift look different from massive galaxies today. They're more compact, more actively star-forming, and have younger stellar populations. Over time, many of these galaxies appear to have undergone quenching, a process where star formation shuts down relatively abruptly. Once quenched, a galaxy consumes its existing gas supply or ejects it, and forms few if any new stars thereafter. It becomes what astronomers call a red and dead galaxy, dominated by old red stars with no young blue stars to brighten it. Understanding why galaxies quench is one of the major questions in galaxy evolution, and Webb's observations of massive early galaxies are providing new insights. Some of these galaxies show signs of powerful outflows, gas being driven out of the galaxy by radiation pressure or stellar winds or energy from the central black hole. These outflows could remove the gas needed for star formation, leading to quenching. Alternatively, some galaxies might simply run out of gas, converting all of it into stars and having nothing left to sustain further star formation. Or the gas might be heated to such high temperatures by feedback processes that it can't cool and collapse to form stars anymore. All of these mechanisms probably operate to varying degrees in different galaxies, and determining which is most important in which circumstances is an active area of research. There's also the fascinating question of whether life could exist in these early massive galaxies. This might seem like a strange tangent, but it connects to deep questions about the emergence of complexity in the universe. Life as we know it requires certain conditions: stable environments, sources of energy, liquid water, organic chemistry. Organic chemistry requires carbon, nitrogen, oxygen, and other heavy elements which are produced in stars. In the very first generation of stars, these elements didn't exist yet. But by the second or third generation, after a few 100 million years, supernovas had enriched the interstellar medium with heavy elements. Rocky planets could form, and at least in principle, the chemistry necessary for life could occur. The massive early galaxies Webb has found are forming stars prolifically between 300 million and 800 million years after the Big Bang. Some of these stars probably have planetary systems, and some of those planets might be inhabitable zones where liquid water can exist. Is it possible that life emerged on one of those planets? We have no way of knowing, of course. Detecting biosignatures in the atmospheres of planets orbiting stars in galaxies billions of light-years away is far beyond our current capabilities. But it's an intriguing thought. If life did emerge in these early massive galaxies, it would have had billions of years to evolve, far longer than life has existed on Earth. Where might such life be now? What might it have become? These are questions for philosophy and speculation more than science, but they remind us that galaxies aren't just collections of stars and gas. They're potential homes for life, for consciousness, for civilizations that might be looking up at their night skies and wondering about the universe just as we are. Another implication of these massive early galaxies relates to the ultimate fate of structure in the universe. The universe is expanding, and that expansion is accelerating due to dark energy. Eventually, in the far future, hundreds of billions of years from now, the acceleration will have become so strong that galaxy clusters will be torn apart. Galaxies will be isolated, unable to see other galaxies, as the space between them expands faster than light can cross. Within each isolated galaxy, assuming it hasn't merged with others before this isolation occurs, life and civilizations could continue. But they'd be cut off from the rest of the universe, unable to observe or interact with anything outside their own galaxy. The massive galaxies forming early in the universe's history might be the ancestors of the galaxies that will exist in this far future. Isolated islands of stars, and perhaps life, alone in an ever-expanding void. This is speculative, of course, but it's part of the broader picture of cosmic evolution, how structures form, evolve, and eventually disperse as the universe ages and changes. Understanding the earliest phases of galaxy formation, the phase Webb is observing, is crucial for understanding this entire history, from the Big Bang to the far future. It's also worth reflecting on the technology that made these discoveries possible. Webb represents decades of work by thousands of engineers, scientists, and technicians. It's one of the most complex machines humans have ever built, with 18 hexagonal mirror segments that had to align to nanometer precision, a sun shield the size of a tennis court that had to unfold flawlessly in space, and instruments cooled to temperatures colder than anywhere in the known universe, except inside laboratory refrigerators. The telescope operates at L2, a gravitationally stable point where it can maintain its position relative to Earth and the Sun with minimal fuel expenditure. It communicates with Earth via radio signals, taking about 5 seconds to travel each way, carrying back data at rates of up to 28 megabits per second. Over its mission lifetime, it will transmit petabytes of data, images, and spectra of thousands of galaxies and other objects. All of this technology, all of this effort, is in service of answering fundamental questions about the universe: where we came from, how structure formed, whether we're alone. The discoveries of massive early galaxies are exactly the kind of result Webb was designed to produce. Observations that challenge our understanding and force us to think more deeply. Every dollar spent, every hour of engineering time, every late night of debugging software or aligning mirrors, it all led to this moment when we're seeing things we didn't expect and learning that the universe is more complex and interesting than we imagined. That's the value of basic research, of scientific exploration without immediate practical applications. You can't predict what you'll discover, but whatever you find expands human knowledge and often leads to unexpected benefits down the line. The technology developed for Webb, the infrared detectors, the cooling systems, the mirror coating techniques, the data processing algorithms, all of these have applications beyond astronomy. And the knowledge itself, understanding how galaxies form and evolve, has value, even if it never leads to practical technology. It enriches our understanding of reality, gives us perspective on our place in the cosmos, and satisfies the basic human drive to explore and understand. As we approach the end of this journey through the mystery of massive early galaxies, it's worth stepping back and appreciating just how remarkable this moment in astronomy is. We're living through a period where our observational capabilities are advancing faster than our theoretical understanding can keep pace. Webb is showing us a universe that's richer and more surprising than we predicted. Other observatories, from ground-based telescopes to space missions studying cosmic rays and gravitational waves, are adding their own pieces to the puzzle. And the result is a picture of the universe that's becoming increasingly detailed and increasingly surprising. Every major advance in astronomy has gone through a similar phase. When Galileo's telescopes revealed moons orbiting Jupiter and phases of Venus, it took time for the astronomical community to accept these observations and develop theories to explain them. When Hubble discovered that the universe is expanding, it contradicted the prevailing belief in a static, eternal cosmos, and it took years for the Big Bang model to be developed and accepted. When the cosmic microwave background was discovered in 1965, it provided strong evidence for the Big Bang, but it also raised new questions about how structure formed in an initially smooth universe. Those questions took decades to answer, through a combination of improved observations and better theoretical models. Now, we're in the midst of another such period. Webb's observations of massive early galaxies are telling us that something about our models of galaxy formation is incomplete. We don't yet know exactly what that something is, whether it's star formation efficiency, stellar populations, dark matter physics, cosmological parameters, or something we haven't thought of yet. But we'll figure it out. Astronomers around the world are working on this problem, analyzing Webb's data, running simulations, developing new theories. within a few years, we'll have a much clearer picture. We'll understand why these galaxies grew so massive so quickly, what processes were at work, and what it tells us about the early universe. And when we do, it will represent a genuine advance in human knowledge, a deeper understanding of the cosmos and how it works. That's something to feel good about, to feel proud of, as members of a species capable of curiosity and exploration. We're tiny, living on a small planet orbiting an ordinary star in one galaxy among trillions. But we're able to study the entire observable universe, to reconstruct its history, to understand how it evolved from simple beginnings to the complex structures we see today. That's extraordinary, and it should fill us with wonder. The 300 galaxies that shouldn't exist are reminders of this wonder. They're evidence that the universe still has secrets to reveal, still has the capacity to surprise us. They're challenges, inviting us to think more carefully and observe more precisely. They're opportunities to make progress, to refine our theories, to get closer to truth. And they're beautiful in their own way. Not beautiful in the way a sunset or a mountain range is beautiful, but beautiful in the way a mathematical proof or a scientific theory is beautiful, elegant, surprising, revealing deep truths about reality. The story of these galaxies is ongoing. More observations will be made, more data will be analyzed, more theories will be developed and tested. The mystery will eventually be solved, though the solution will likely raise new questions, as solutions always do in science. And future astronomers will look back on this period as a turning point. A moment when Webb's observations forced cosmology to evolve, to incorporate new understanding about the early universe. That evolution is happening now, in real time, and we're fortunate to be witnessing it. So thank you again for taking this journey with me through the early universe and the mystery of massive galaxies. It's been a privilege to share this story, to explore these questions, to wonder at the complexity and richness of the cosmos. If this exploration resonated with you, if it sparked curiosity or wonder or a desire to learn more, please consider liking this video and subscribing to the channel. Your support makes it possible to continue creating these in-depth explorations of space, time, and the universe. And the next time you look up at the stars, remember that you're looking back in time, seeing light that began its journey years or millennia or billions of years ago. Some of that light comes from galaxies that formed when the universe was impossibly young, galaxies that assembled more stars in a few 100 million years than should have been possible. They exist, despite our models saying they shouldn't. They challenge our understanding and invite us to learn more, and that's precisely what makes them so fascinating, so important, and so beautiful. The universe is under no obligation to be easily understood, but it rewards those who look carefully and think deeply. These 300 impossible galaxies are proof of that. They're real, they're out there, and they're waiting for us to figure them out. Good night, and may your curiosity never stop growing. But there's one more dimension to this story that we need to explore, a dimension that connects these ancient galaxies to our own existence in ways that are both profound and unsettling. Let's talk about time itself, and what it means that we're observing these galaxies as they were billions of years ago. When we look at a galaxy at redshift 10, we're seeing it as it was about 13.2 billion years ago. The light we're detecting left that galaxy when the universe was only 480 million years old. It's been traveling through space ever since, crossing billions of light years, finally arriving at Webb's mirrors where it gets focused, analyzed, and turned into data. But here's the thing. That galaxy doesn't look like that anymore. In the 13.2 billion years since the light left, that galaxy has continued evolving. It's merged with other galaxies, formed new generations of stars, perhaps had its star formation quenched, evolved into a massive, elliptical galaxy, or been absorbed into an even larger structure. We have no way of knowing what it looks like today, right now, in its own present moment. And, in fact, the very concept of right now across cosmic distances becomes problematic once you account for relativity. There's no universal now, no cosmic clock ticking simultaneously everywhere. Time is relative. It depends on motion and gravity, and across billions of light years, the notion of simultaneity breaks down completely. The galaxy we're observing had its own timeline, its own sequence of events unfolding according to the laws of physics. Some of those events happened in what we call the past, like the light we're seeing now that left 13.2 billion years ago. Other events happened later in the galaxy's history, but are still in our past. Light that left 10 billion years ago, or 5 billion years ago. Light that hasn't reached us yet, but will arrive thousands or millions of years from now. And still other events are happening in the galaxy's present, whatever that means. Events whose light won't reach Earth for billions of years, long after the sun has died and Earth has become uninhabitable. This temporal disconnection is one of the strangest consequences of cosmic distances and the finite speed of light. We're observing a universe that no longer exists in the form we're seeing it. Every distant galaxy is a fossil, a preserved moment from the past. The further we look, the further back in time we see, until at the very edge of the observable universe, we're seeing light from just a few 100 million years after the Big Bang. But all of those distant galaxies, if they still exist, have continued evolving throughout the billions of years it took their light to reach us. This creates a strange situation where astronomers studying galaxy evolution are looking at snapshots from different times and trying to piece together a coherent story. It's like trying to understand human development by looking at photographs of different people at different ages. You see an infant here, a toddler there, a teenager, an adult, an elderly person. You can make inferences about how humans age, but you're not watching any individual person grow up. You're looking at different individuals at different stages. Similarly, when astronomers look at galaxies at different redshifts, they're looking at different galaxies at different ages. They try to identify patterns, to figure out which young galaxies might evolve into which old galaxies. But there's no way to directly watch an individual galaxy evolve over billions of years. The timescales are simply too long. This is why finding massive galaxies at high redshift is so important and so troubling. It suggests that some galaxies evolved very rapidly in their youth, going through changes in a few 100 million years that other galaxies took billions of years to undergo. And if that's true, it means galaxy evolution is more diverse, more complex, more dependent on initial conditions and environment than our simplified models assume. Some galaxies take the slow path, gradually accumulating mass over billions of years. Others take the fast path, growing explosively in their early history and then settling down. Understanding why some galaxies follow one path and others follow a different path is crucial to understanding galaxy evolution as a whole. Now, let's consider the measurements themselves, the actual process by which astronomers extract information from the photons collected by Webb's mirrors. When light enters Webb's telescope, it travels through a complex optical system designed to focus it precisely onto detectors. The primary mirror, composed of 18 hexagonal segments, collects the light. The secondary mirror, a smaller convex mirror suspended in front of the primary, reflects the light back toward the primary. The light then passes through a hole in the center of the primary mirror and enters one of Webb's instruments. Webb has four main instruments: NIRCam, the near-infrared camera; NIRSpec, the near-infrared spectrograph; MIRI, the mid-infrared instrument; and NIRIS, the near-infrared imager and slitless spectrograph. Each instrument is optimized for different types of observations. NIRCam takes wide-field images in near-infrared wavelengths from 0.6 to 5 microns. It's the instrument that produced most of the stunning early deep-field images, the ones showing thousands of galaxies in exquisite detail. NIRSpec can take spectra of up to 100 objects simultaneously using a microshutter array, a device containing thousands of tiny shutters that can be individually opened or closed to select which object's light gets analyzed. MIRI observes at longer wavelengths, from 5 to 28 microns, which is important for studying cool dust and gas. And NIRIS specializes in studying exoplanet atmospheres through transit spectroscopy, though it can also observe galaxies. When observing distant galaxies, astronomers typically start with imaging to identify interesting targets. They'll point Webb at a carefully selected region of sky, often a field that's been extensively studied by other telescopes like Hubble, and take deep exposures lasting many hours. These images reveal thousands of galaxies, from nearby bright ones to extremely distant faint ones. The faintest galaxies in Webb's deep fields are detected at magnitudes around 30 or 31, which is extraordinarily faint. To give you a sense of scale, the human eye can see stars down to about magnitude 6 under ideal dark sky conditions. Magnitude 10 requires a decent amateur telescope. Magnitude 20 requires a professional observatory telescope, and magnitude 30 requires a space telescope with exquisite sensitivity observing for many hours. At magnitude 30, the detected photon rate is minuscule, perhaps a few photons per hour across all of Webb's collecting area. Detecting such faint objects requires not just large mirrors and sensitive detectors, but also careful data processing to distinguish real sources from noise. Once the imaging is complete, astronomers analyze the images to create catalogs of objects, measuring each galaxy's position, brightness, size, and shape. They then select interesting targets for follow-up spectroscopy. Spectroscopy is where the real information lies, but it's expensive in terms of observing time. Getting a good spectrum of a faint, high-redshift galaxy can take tens of hours, so astronomers have to choose their targets carefully. They prioritize galaxies that appear particularly distant based on their colors, or particularly massive based on their brightness, or particularly interesting for other reasons, like unusual morphologies or potential gravitational lensing. When spectroscopy is obtained, it reveals detailed information about the galaxy. The spectrum shows absorption lines, where light has been absorbed by atoms in the galaxy's stars. Each element produces characteristic absorption lines at specific wavelengths. So, by identifying which lines are present, astronomers can determine the galaxy's chemical composition. The redshift of these lines tells you how much the universe has expanded since the light was emitted, which gives you the galaxy's distance and the cosmic time at which you're observing it. The spectrum also shows emission lines, bright features where light is being emitted by ionized gas in star-forming regions or around the central black hole. These emission lines provide information about the physical conditions in those regions: temperature, density, ionization, state, velocity. By analyzing emission lines from different parts of the galaxy, astronomers can map out how gas is moving within the galaxy whether it's rotating in an organized disk or moving in more chaotic ways. They can measure the rate at which stars are forming by looking at emission lines from hot young stars and ionized gas around them. They can detect the presence of an active supermassive black hole by looking for emission lines characteristic of the intense radiation environment near a black hole. All of this information comes from careful analysis of the spectrum, comparing observed wavelengths and intensities to theoretical models and laboratory measurements of atomic physics. It's painstaking work, requiring expertise in observational astronomy, atomic physics, and radiative transfer theory, but it's how we learn about galaxies too distant to visit. The spectra themselves are often noisy, with low signal-to-noise ratios, especially for the faintest galaxies. Extracting reliable information requires sophisticated statistical techniques and careful validation against known sources and simulations. This is one reason why early photometric redshift estimates sometimes get revised when spectroscopy becomes available. The photometric estimates are based on measuring the galaxy's brightness in several broad wavelength bands and fitting to models, but they involve assumptions that aren't always correct. Spectroscopy is more reliable because it actually measures the positions of specific spectral features, but it's also more challenging and time-consuming. As Webb accumulates more observing time, the number of high redshift galaxies with spectroscopic confirmation is growing steadily. We're building up a statistical sample that allows for more robust conclusions about the galaxy population at different cosmic times. This sample is revealing not just the presence of massive early galaxies, but also the diversity among them. Some are actively forming stars at prodigious rates, while others appear to have already quenched and contain mostly old stellar populations. Some show clear signs of ongoing mergers with disturbed morphologies and multiple nuclei, while others appear relatively relaxed and organized. Some have central supermassive black holes that are actively accreting and producing powerful radiation, while others show no sign of black hole activity. This diversity suggests that even in the early universe, within the first billion years, galaxies were following multiple evolutionary paths. There wasn't a single universal trajectory that all galaxies followed, but rather a range of possibilities, depending on the galaxy's mass, its environment, its merger history, and perhaps other factors we don't fully understand yet. Understanding this diversity is just as important as understanding the average properties, because it tells us about the range of physical processes operating in the early universe. Another crucial aspect of Webb's observations is what they reveal about the intergalactic medium, the gas filling the space between galaxies. In the early universe, this gas was initially neutral hydrogen left over from recombination. As the first stars and galaxies formed, their ultraviolet radiation began ionizing this hydrogen, creating bubbles of ionized gas around each galaxy. These ionization bubbles grew and merged over time, eventually overlapping until the entire universe was reionized. But the process wasn't uniform. Some regions ionized earlier because they contained more galaxies, producing more radiation. Other regions remained neutral, longer, because they were voids, under-dense regions with few galaxies. Webb can probe this process by observing how light from distant galaxies is absorbed by neutral hydrogen along the line of sight. Neutral hydrogen absorbs light at a specific wavelength called Lyman alpha, about 121.5 nanometers in the rest frame. Because of the expansion of the universe, this absorption gets redshifted to longer wavelengths we can observe. If there's a lot of neutral hydrogen between us and a distant galaxy, we'll see strong absorption at the redshifted Lyman alpha wavelength. If the intergalactic medium is mostly ionized, we'll see little absorption. By studying this absorption in the spectra of many galaxies at different redshifts, astronomers can map out how reionization progressed over time. The observations suggest that reionization was largely complete by about 1 billion years after the Big Bang, corresponding to redshift around 6. At redshifts above 6, there's increasing evidence for neutral hydrogen, suggesting that earlier times correspond to the epoch of reionization itself. At the highest redshifts, Webb can observe, around redshift 12 to 14, we're seeing the very tail end of the Dark Ages and the beginning of reionization. This is why finding galaxies at these extreme redshifts is so valuable. They're illuminating a critical transition in the universe's history. The massive galaxies Webb has found are significant contributors to reionization. Their copious star formation produces abundant ultraviolet radiation that ionizes the surrounding hydrogen. The fact that there are more massive galaxies than expected means there was more ionizing radiation than expected, which might explain why reionization appears to have occurred efficiently and relatively quickly. But there are complications. Not all ultraviolet photons produced by stars escape from their galaxies to ionize the intergalactic medium. Some are absorbed by dust within the galaxy. Some are absorbed by neutral hydrogen within the galaxy itself. The fraction that escapes, called the escape fraction, is a critical parameter for understanding reionization, and it's still poorly constrained observationally. Webb is helping to measure escape fractions by comparing the ultraviolet radiation detected from galaxies to theoretical predictions of how much should be produced based on the star formation rate. The early results suggest that escape fractions in early galaxies might have been higher than in local galaxies, perhaps because early galaxies had less dust and more porous structures that allowed radiation to escape more easily. If confirmed, this would help explain how reionization occurred as quickly as it did, despite the universe's enormous volume. There's also the question of what astronomers call cosmic variance, the statistical uncertainty that comes from observing only a limited region of the universe. The observable universe is enormous, but Webb can only observe small patches of it at high resolution. If those patches happen to be unusual, either overdense or underdense, compared to the average, then conclusions drawn from them might not represent the universe as a whole. Early on, there was concern that the massive galaxies Webb was finding might be concentrated in unusual regions, that the observations were biased toward overdense areas where galaxy formation occurred more efficiently. But as Webb has observed more independent fields covering different regions of the sky, the pattern has held up. Massive galaxies appear consistently across all observed fields, suggesting that they're a genuine feature of the high redshift universe rather than a statistical fluke. Still, cosmic variance remains a consideration, and will until Webb has surveyed a large enough area to average over the universe's large-scale structure. Plans are underway for wide-area surveys that will observe larger regions of sky at moderate depth, complementing the existing ultra-deep observations of small fields. These surveys will provide better statistics and reduce cosmic variance uncertainty. Let's turn now to the question of how these discoveries are being communicated to the broader public and what misconceptions have arisen. When the first images and results from Webb were released, they generated enormous public interest. The images themselves are stunning, with incredible detail and vibrant colors showing galaxies in unprecedented clarity. But there were also sensational headlines about Webb-breaking cosmology or disproving the Big Bang. These headlines were exaggerations, sometimes based on preliminary results that later got revised, sometimes based on misunderstandings of what the observations actually showed. The reality, as we've discussed, is more nuanced. Webb has found something surprising. More massive galaxies in the early universe than our models predicted. This doesn't break cosmology or disprove the Big Bang. It means our models of galaxy formation within the Big Bang framework need refinement. Big Bang cosmology as a whole is supported by multiple independent lines of evidence. The expansion of the universe, the cosmic microwave background, the abundances of light elements, the large-scale structure. Finding that galaxies formed faster than expected doesn't contradict any of this. It just means we didn't fully understand one particular process. How gas turns into stars in the early universe. This distinction is important because there's a lot of public confusion about how science works, about the difference between a theory being wrong and a theory needing refinement. All scientific theories are approximations, simplified models that capture the most important features of reality while ignoring details that are less important or poorly understood. When new observations reveal that some of those details are actually important, the theory gets refined to include them. This is progress, not failure. It's how science advances. Newton's theory of gravity was an excellent approximation that worked beautifully for centuries, but it was incomplete. Einstein's general relativity refined it, incorporating effects that Newton's theory couldn't account for. That didn't mean Newton was wrong. It meant his theory was an approximation that worked well in most circumstances, but needed refinement for extreme situations like very strong gravity or very high speeds. Similarly, our current models of galaxy formation are good approximations that work well for most situations, but they need refinement to account for the rapid formation of massive galaxies in the early universe. That's what astronomers are working on now, and that work is proceeding normally within the scientific process. But this nuance sometimes gets lost in public communication, especially in headlines designed to grab attention. Webb confirms massive early galaxies doesn't generate as many clicks as Webb breaks the Big Bang, even though the former is accurate and the latter is misleading. As consumers of science news, it's important to be aware of this tendency and to dig deeper than headlines, to read the actual research papers, or at least careful science journalism that explains what was really found and what it means. Astronomy is a field where almost every major discovery initially generates more questions than answers. That's not a bug, it's a feature. It's how we make progress. We observe something unexpected. We develop hypotheses to explain it. We make predictions based on those hypotheses. We test them with new observations. The cycle continues, and our understanding gradually becomes more complete and more accurate. Webb's observations of massive early galaxies are right in the middle of this cycle. We're past the initial surprise. We're developing hypotheses, and we're beginning to test them. Over the next few years, as more data accumulates and as theoretical models improve, we'll converge on an explanation. And then, attention will shift to the next mystery, the next observation that doesn't fit our models, the next opportunity to learn something new. This brings us to a broader question. Why does any of this matter? Why should anyone care about galaxies that formed billions of years ago, so far away that their light takes most of the age of the universe to reach us? There are several answers, and they operate at different levels. At the most fundamental level, understanding the universe is intrinsically valuable. Humans are curious creatures. We want to know how things work, where we came from, what the nature of reality is. These are deep questions that every culture has grappled with throughout history. Modern cosmology provides scientific answers to these questions, answers based on observation and mathematical modeling rather than mythology or speculation. Those answers have value in themselves as contributions to human knowledge and understanding. At a more practical level, the technology developed for telescopes like Webb has applications beyond astronomy. Infrared detectors, lightweight mirror coatings, precision actuators, data compression algorithms, all of these technologies were developed or refined for astronomical applications and then found uses elsewhere. Medical imaging devices, industrial quality control systems, communications technology, even consumer electronics have benefited from innovations originally driven by astronomy. You can't predict ahead of time which technologies will prove useful, but history shows that investments in basic science consistently generate unexpected technological spin-offs. At a societal level, astronomy provides perspective. Understanding that we live on a small planet orbiting an ordinary star in a vast universe filled with billions of galaxies affects how we see ourselves and our place in the cosmos. It can be humbling, yes, but it can also be inspiring. It reminds us that we're part of something much larger than our immediate concerns, that the universe is ancient and enormous and filled with wonders. This perspective can encourage long-term thinking, environmental responsibility, international cooperation, all values that become more important as humanity faces global challenges. And, at an educational level, astronomy captures people's imagination in ways that few other sciences do. The stunning images from Hubble and now Webb, the mind-bending concepts like black holes and dark matter, and the Big Bang, the sheer scale of cosmic distances and timescales, all of this naturally engages curiosity and inspires young people to pursue careers in science and engineering. Many scientists in various fields got their start by looking at pictures of galaxies and nebulas and deciding they wanted to understand how the universe works. So when we spend billions of dollars building a telescope and launching it into space, we're not just buying pretty pictures. We're advancing human knowledge, developing new technologies, providing perspective and inspiration, and training the next generation of scientists and engineers. The specific discoveries, like the massive early galaxies, are valuable not just in themselves, but as steps in this broader process. Each discovery leads to new questions, new hypotheses, new observations, keeping the cycle of scientific progress moving forward. And sometimes, though rarely, a discovery is so profound that it changes our entire worldview, revealing something about reality that we never suspected. We don't know yet whether the massive early galaxies will prove to be such a discovery. They're certainly surprising and important, but are they revolutionary? That depends on what explanation turns out to be correct. If the solution is relatively prosaic, higher star formation efficiency, or larger stellar masses in the early universe, then it's an important refinement of our models, but not a paradigm shift. If the solution requires changing fundamental aspects of cosmology, like the properties of dark matter or the nature of dark energy, then it could be revolutionary, reshaping our understanding of the universe at the most basic level. We won't know until the work is done, until enough observations have accumulated and enough theoretical models have been tested that a consensus emerges. That's the nature of frontier science. You're working in areas where the answers aren't known yet, where multiple possibilities remain open, where uncertainty is high. It can be frustrating, but it's also exciting because you're genuinely exploring unknown territory, making discoveries that no one has made before. The astronomers analyzing Webb's data, the theorists developing new models, the engineers planning the next generation of telescopes. They're all part of this grand endeavor to understand the universe. Their work will be remembered long after current political debates and economic concerns have faded from memory. In 1,000 years, assuming civilization survives and continues advancing, people will look back on the early 21st century as the time when humanity really began to understand the cosmos in detail. When we mapped the cosmic microwave background, detected gravitational waves, imaged black holes, found thousands of exoplanets, and yes, discovered massive galaxies in the early universe that challenged our theories and forced us to develop better ones. These discoveries are part of humanity's intellectual heritage, contributions to knowledge that will be built upon by future generations for centuries or millennia to come. That's worth investing in, worth celebrating, worth explaining to the public so that everyone can appreciate what we're learning about the universe we inhabit. And that's why, ultimately, the story of these 300 impossible galaxies matters. Not just because they're unexpected or because they challenge our models, but because they're part of the ongoing human quest to understand reality, to figure out where we came from and how the universe works. Every generation contributes to this quest in its own way, building on what came before and setting the stage for what comes after. We're fortunate to be living in a time when our technology has advanced to the point where we can observe the universe in unprecedented detail, seeing things that previous generations could only dream about. And we're fortunate that there are still mysteries to solve, still surprises waiting to be discovered, still opportunities to expand human knowledge. The 300 galaxies that Webb has found, galaxies that formed faster and grew larger than our theories predicted, are exactly such a mystery. They're challenging us, inviting us to think more carefully, to observe more precisely, to develop better theories. And in rising to that challenge, we're doing what humans have always done, pushing the boundaries of knowledge, exploring the unknown, and gradually building a more complete and accurate understanding of the cosmos we inhabit. That work is ongoing. It will continue long after Webb's mission ends, and it will involve new telescopes, new technologies, new discoveries that we can't even imagine yet. But for now, in this moment, we have Webb's observations of the early universe, revealing a cosmos that's more dynamic, more surprising, and more fascinating than we expected. We have 300 galaxies that shouldn't exist, but do, and we have the opportunity to figure out why, to solve the mystery, to add another piece to the grand puzzle of cosmic evolution. That's where we are in this story, right at the beginning of understanding what these observations mean and what they tell us about the universe. The ending hasn't been written yet, because the research is still underway. The data is still being analyzed. The theories are still being developed. But when the ending does come, when we finally understand why massive galaxies form so early and so efficiently, it will represent a genuine advance in human knowledge. It will be a moment worth celebrating, a victory for curiosity and careful observation and rigorous thinking. And it will set the stage for the next mystery, the next observation that doesn't fit, the next opportunity to learn something new about the cosmos. Because that's how science works, always moving forward, always pushing into new territory, always revealing that the universe is richer and more complex than we imagined. The 300 impossible galaxies are proof of that. They exist, despite our models saying they shouldn't. And in figuring out how they came to exist, we'll learn something profound about how the universe works. That's the promise and the challenge that Webb's observations have given us. It's a gift, really, an invitation to deepen our understanding, to refine our theories, to get closer to truth. And it's a reminder that no matter how much we learn, the universe always has more to teach us. We just have to keep looking, keep wondering, and keep asking questions. Good night. And may you never lose your sense of wonder at the mysteries of the cosmos. Actually, there's one more thing we should talk about before we close. Something that ties together all the threads we've explored tonight. The connection between these early massive galaxies and the question of life in the universe. Because if galaxies formed faster and more efficiently than we thought, if stars began forming earlier and in greater numbers, that has implications for when and where life could have emerged. Life as we know it requires certain conditions. It needs liquid water, which means temperatures between 0 and 100 degrees Celsius at reasonable pressures. It needs sources of energy, like sunlight or chemical reactions. It needs organic chemistry, carbon-based molecules that can form complex structures. And crucially, it needs time. Time for simple molecules to become complex, for complex molecules to become self-replicating, for self-replication to evolve into the sophisticated machinery of life. On Earth, life emerged relatively quickly after the planet formed. Earth is about 4.6 billion years old, and evidence for life extends back at least 3.8 billion years, possibly earlier. So within the first billion years of Earth's history, life arose and established itself. That suggests that given the right conditions, the transition from chemistry to biology can happen fairly rapidly on cosmic timescales. Now, the elements needed for life, carbon, nitrogen, oxygen, phosphorus, sulfur, weren't present in the early universe. They had to be created in stars through nucleosynthesis and then spread through space by supernova explosions. The first generation of stars, population, 3 stars, formed from pure hydrogen and helium. When they exploded, they enriched the surrounding gas with the first heavy elements. The second generation could form with some heavy elements, enough to create rocky planets and perhaps support life. If the massive early galaxies Webb has discovered were forming stars prolifically between 300 million and 800 million years after the Big Bang, those stars were enriching their galaxies with heavy elements much faster than we thought possible. By 1 billion years after the Big Bang, some of these galaxies might have had chemical compositions similar to galaxies today. Enough carbon and oxygen and other elements to support complex chemistry. Rocky planets could have formed around second or third generation stars, and at least in principle, life could have emerged on those planets. If it did, that life has had 12.8 billion years to evolve. For comparison, life on Earth has had 3.8 billion years. And in that time, it's gone from single-celled organisms to the complexity and diversity we see today, including intelligent, technological civilization. What might life achieve given 12.8 billion years, more than 3 times as long as Earth-based life has had? We can't answer that question with any certainty. Of course, evolution doesn't follow a predictable trajectory, and we don't know whether intelligence and technology are inevitable outcomes or rare accidents. But it's thought-provoking to consider. If life emerged in those early massive galaxies, if it survived and evolved and eventually became intelligent, such civilizations would be inconceivably old and advanced by now. They might have explored their entire galaxies, developed technologies we can't even imagine, perhaps even found ways to influence the evolution of their galaxies or detect and communicate with other civilizations. Some scientists have speculated that truly advanced civilizations might leave detectable signatures on galactic scales. megastructures that harvest the energy of millions or billions of stars, or engineered changes to the properties of their galaxies. Webb hasn't detected anything like that. The galaxies we observe appear natural, governed by physics rather than engineering. But that doesn't rule out the existence of advanced civilizations. It just means they're either not modifying their galaxies on scales we can detect, or they're using technologies and approaches we wouldn't recognize as artificial. This connects to a broader question about the prevalence of life in the universe. The Fermi paradox, named after physicist Enrico Fermi, asks if the universe is so old and so large, and if life can emerge relatively easily given the right conditions, then where is everybody? Why haven't we detected signs of extraterrestrial intelligence despite decades of searching? There are many proposed answers to this paradox. Maybe life is rare, requiring a very specific combination of conditions that exists on few planets. Maybe intelligence is rare. Most life remains simple and never develops complex nervous systems and cognition. Maybe technological civilizations are short-lived, typically destroying themselves through war, environmental collapse, or other catastrophes, shortly after developing advanced technology. Maybe they exist, but are too far away for us to detect, separated by distances too vast for communication or travel. Maybe they exist and have visited our solar system, but haven't contacted us for their own reasons. Maybe they're out there broadcasting signals right now, but we're not listening at the right frequencies or looking in the right directions. Or maybe the Fermi paradox is based on incorrect assumptions. Maybe intelligence and technology aren't as inevitable as we assume. Maybe the transition from simple life to complex multicellular life, or from multicellular life to intelligence, involves bottlenecks that are extremely unlikely to cross. The discovery of massive early galaxies doesn't answer the Fermi paradox, but it does affect how we think about it. If galaxies and stars were forming earlier and more abundantly than we thought, then planets were presumably forming earlier too, and potentially life. That pushes back the timeline for when life could have emerged in the universe, giving it more time to spread and evolve. On the other hand, those early galaxies were violent places, with intense star formation, frequent supernovas, strong radiation fields. Planets in such environments might be sterilized repeatedly by nearby supernovas or exposed to dangerous levels of radiation from young massive stars. Maybe life had difficulty getting established in those early galaxies. Maybe it had to wait until things calmed down before stable ecosystems could develop. We simply don't know. And without finding actual evidence of life elsewhere, either through direct detection of biosignatures in exoplanet atmospheres or through receiving signals from extraterrestrial civilizations, we can only speculate. But the question is fascinating, and it's one that Webb and other telescopes are helping to address by revealing the conditions that existed in the early universe. Webb is also contributing to the search for life through its observations of exoplanets, planets orbiting other stars. While its primary mission is studying the early universe, Webb has dedicated time for observing exoplanets transiting in front of their stars. During a transit, some of the star's light passes through the planet's atmosphere on its way to us. Different molecules in the atmosphere absorb light at specific wavelengths, creating an absorption spectrum that reveals what the atmosphere is made of. Webb has already detected water vapor, carbon dioxide, methane, and other molecules in the atmospheres of several exoplanets. Most of these are giant planets, Jupiter-sized or larger, not candidates for life as we know it. But the techniques are being refined, and in the future, Webb will observe smaller, potentially habitable planets around nearby stars. If it detects the right combination of molecules, oxygen, and methane together, for instance, it might indicate biological processes maintaining those gases in the atmosphere. That would be indirect evidence for life, not proof. You'd need more observations to rule out non-biological explanations, but it would be the most significant hint we've ever had that life exists beyond Earth. This connects back to our broader theme, understanding the universe and our place in it. The massive early galaxies tell us about the early history of the cosmos, how structure formed and evolved, how the universe transitioned from the smooth, nearly uniform state after the Big Bang to the complex web of galaxies and voids we see today. The search for exoplanets and biosignatures tells us about the prevalence of planets and potentially life. And together, these different lines of investigation are building a comprehensive picture of the universe, its history, its contents, and our place within it. It's a picture that's become increasingly detailed over the past century as our observational capabilities have improved. 100 years ago, in the 1920s, we didn't even know galaxies existed as separate objects. The Milky Way was thought to be the entire universe. Then Hubble discovered that fuzzy nebulas were actually distant galaxies, and the universe suddenly became vastly larger than anyone had imagined. He also discovered that the universe is expanding, leading to the Big Bang theory. 50 years ago, in the 1970s, we had just confirmed the Big Bang through the discovery of the cosmic microwave background. We were beginning to understand galaxy formation through computer simulations. We were debating whether dark matter existed and what it might be. 25 years ago, in the late 1990s, we discovered dark energy through observations of distant supernovas. We confirmed that the universe's expansion is accelerating, driven by some unknown energy field. We were just beginning to detect the first exoplanets around other stars. Today, we have telescopes like Webb, revealing the universe in unprecedented detail. We've mapped the cosmic microwave background exquisitely, constraining cosmological parameters to percent-level precision. We've detected gravitational waves from merging black holes and neutron stars, opening an entirely new window on the universe. We've imaged the shadow of a black hole, confirming predictions of general relativity in the strongest gravitational fields that exist. And we've found thousands of exoplanets, showing that planetary systems are common and diverse. Each generation has pushed our understanding further, and there's no reason to think this progress will stop. The next generation of telescopes is already being planned and built. The extremely large telescope in Chile will have a 39-meter mirror able to directly image exoplanets and study their atmospheres in detail. The Nancy Grace Roman Space Telescope will conduct wide-field surveys, mapping billions of galaxies and searching for exoplanets through gravitational microlensing. Future space telescopes might be even larger than Webb, with mirrors 10 or 15 meters across, able to observe the very first stars that formed in the universe. Concepts for telescopes on the Moon are being explored, taking advantage of the Moon's stable surface and lack of atmosphere. And, perhaps, someday, centuries from now, we'll have telescopes in space large enough to directly image Earth-like planets around nearby stars, not just detecting them indirectly, but actually seeing them as resolved disks with continents and oceans and clouds. We might even detect technosignatures, signs of advanced civilizations modifying their planets or solar systems in detectable ways. All of this is speculative, of course. We can't predict what technologies will be developed or what discoveries will be made. But the trajectory is clear. Our understanding of the universe has deepened dramatically over the past century, and there's every reason to expect that trend to continue. The massive early galaxies that Webb has discovered are just the latest surprise in this ongoing story. They're challenging us to refine our theories, to think more carefully about how the universe works. And in meeting that challenge, we're continuing the great project of human civilization, building knowledge, exploring the unknown, pushing back the boundaries of ignorance. This project has been ongoing for millennia, from ancient astronomers tracking the motions of planets to medieval scholars preserving and translating scientific texts, to Renaissance thinkers developing the scientific method, to Enlightenment scientists measuring the speed of light and the size of the solar system, to 19th century astronomers mapping the Milky Way, to 20th century cosmologists discovering the Big Bang and dark matter and dark energy. And now in the 21st century, we're using space telescopes to observe galaxies from when the universe was young, finding things we didn't expect, learning that the cosmos is more complex and more interesting than we imagined. Every generation has contributed to this accumulating body of knowledge, each building on what came before. And we're fortunate to be living in a time when the pace of discovery is particularly rapid, when new technologies are revealing aspects of the universe that were completely inaccessible to previous generations. The questions we're asking now, about how galaxies formed in the first billion years, about whether life exists elsewhere, about the nature of dark matter and dark energy, these are profound questions that go to the heart of understanding reality. And while we don't have complete answers yet, we're making progress, observation by observation, theory by theory, gradually building a more complete picture. That's what the 300 massive early galaxies represent. A piece of the puzzle, a clue to how the universe works, a challenge to our understanding that will ultimately lead to deeper knowledge. They're reminders that the universe is vast and ancient and full of wonders, that we're only beginning to understand it, and that every answer raises new questions. That can be frustrating, yes, but it's also exhilarating. It means there's always more to learn, always new mysteries to explore, always opportunities for discovery. And it means that future generations will look back on our time as a period of rapid scientific advancement, when humanity transitioned from knowing very little about the cosmos to having a detailed understanding of its history, structure, and contents. We're living through that transition right now, witnessing discoveries that will be remembered for centuries. The massive early galaxies are part of that story, a chapter in humanity's ongoing quest to understand the universe. And whether you're an astronomer analyzing Webb data, a student learning about cosmology, or simply someone looking up at the stars and wondering what's out there, you're part of that quest too. Because science isn't just something that happens in universities and observatories, it's a human endeavor, a collective effort to understand reality. And everyone who takes an interest, who learns about the universe, who asks questions and thinks carefully about the answers, is contributing to that effort. So yes, there are 300 galaxies that shouldn't exist according to our models, but do. Yes, they're challenging our understanding and forcing us to develop better theories. Yes, there's still uncertainty about what they mean and how they formed. But that's not a problem. It's an opportunity. An opportunity to learn, to grow, to deepen our understanding of the cosmos. And ultimately, an opportunity to appreciate just how remarkable it is that we, evolved primates on a small planet, are able to observe and understand galaxies billions of light years away. Galaxies that formed when the universe was young and will continue existing long after our sun has died. That's extraordinary, and it should fill us with wonder and with gratitude that we live in a time when such knowledge is accessible. Thank you for joining me on this journey through the mystery of massive early galaxies, and what they tell us about the universe. It's been a privilege to share this story with you, to explore these questions together, to contemplate the vastness and complexity of the cosmos. If you've found value in this exploration, if it's sparked curiosity or wonder or a desire to learn more, I encourage you to like this video and subscribe to the channel. Your support makes it possible to continue creating these deep dives into space, time, cosmology, and the fundamental nature of reality. And the next time you look up at the night sky, remember what you've learned tonight. That the light you're seeing left distant stars and galaxies years or even billions of years ago. That some of those galaxies formed impossibly early, growing to massive sizes in just a few 100 million years through processes we're still working to understand. That they challenge our theories and invite us to think more deeply about how the universe works. And that by studying them, by rising to the challenge they represent, we're continuing the great human project of building knowledge and understanding reality. The universe is under no obligation to be simple or easily comprehended, but it rewards careful observation and rigorous thinking. These 300 impossible galaxies are proof of that. They exist, despite our predictions. They're real, they're fascinating, and they're teaching us something new about the cosmos. That's what makes them so valuable, so important, and so beautiful. Not beautiful in a conventional sense, but beautiful in the way that any profound truth is beautiful, revealing deep patterns in the nature of reality. So keep looking up, keep wondering, keep asking questions. The universe is vast and ancient and full of mysteries, and there's always more to discover. These massive early galaxies are just one mystery among many, and solving it will lead to new mysteries, new questions, new opportunities for understanding. That's the nature of science, always moving forward, always revealing that reality is richer and more complex than we imagined. And it's a journey worth taking, whether you're a professional astronomer or simply someone who looks up at the stars and wonders what's out there. Good night, and may the cosmos continue to surprise and inspire you.